So my name is Wes Richardet, and I'm giving a talk on searching the spatial data lake. So just a few questions. Who all uses search currently with a show of hands? Okay. Who's used Parquet? All right, Parquet's popular. Does anybody use Postgres or PG Search or FTS? Postgres. Okay, what about Elasticsearch, OpenSearch? Okay, what about Lucene? Okay, cool. All right, so who is Lucene? Who are we? Basically built on the foundation of Apache Lucene, and then continued on. Elasticsearch, Solar came out to help scale out Lucene, and then OpenSearch fork of Elastic occurred, and then now we're building on some of those foundations to tear apart the pieces of search to make it easier, and we're wanting to really focus on going deep in making things like vector, spatial, text, those type of search, improve performance, add features around that. Me personally, I worked on the search team at Planet for a number of years in addition to other things. So if you wrote a bot that spammed the Planet catalog, I was on call for that. So another thing we want to, I think there's a hidden opportunity to add plugins and extend some of these search engines that we can, I think at Lucene help you do. So first thing I want to cover is what problem are we actually trying to solve? What is Lucene? What is GeoParquet? And then how do we go about solving this problem? So I think, 10 plus 15 years ago, 20 years ago, the cloud started emerging and we started using that as an opportunity to run bigger applications. We spun up VMs instead of running servers at an office or at a data center. And we started building more complex, faster, just doing more with other people's computers. And we ran into these problems where we solved it with, caching things in Redis, and then we looked at things like Cassandra or these other bigger, big data, the term started running rampant. And then we started using things like Elasticsearch, Solar, to copy data over to fulfill a different use case of how do I search on my data as opposed to retrieval out of a relational database. And so then we really took it to maybe another extreme where everything became a microservice. We used Kubernetes, DevOps, started with batch processing, then we started everything, the push for real time. So we moved to stream processing, and then we built analytics real time off of that. And then now we've got this ETL that's now ELT problem where we throw all the data in the data lake and then we want to transform it on the fly. But the problem is that the cheap storage is not so cheap anymore for a couple of reasons of prices going up, but also we've got way more data. So this isn't a talk about what's better than the other. It's about there's some consolidation and some budget constraint that we want. The services we do run, we're not going to replace them. That costs way too much downtime. How can we extend them? How can we get them to do more? And so you see a lot of things like Postgres getting a ton of new extensions, things like CockroachDB and that implementing the Postgres protocol so that people can easily migrate between different use cases. And you hear some of these stories of how expensive it is to actually quit or delete from object storage. So you kind of just stay there and kick the can down the road. And, going back to private data centers or on-prem or moving it outside of some of the other clouds is also kind of disadvantaged at the moment. And so a lot of times, and especially in my experience, we always said, if you want to search on it, just copy all the data in. Well, that was like an automatic near doubling or or more. So it's kind of a tough practice to do, and you eventually collapse under your own weight where you're running so many services, so much data that you start having these, I guess I'll call it like day two problems of, being victim to the decisions you made. And so now kind of a concept of this talk is like leave the data where it is. So there's this consolidation going on where the data is maybe put on object storage or in a volume, the kind of the lake house idea of it's put in one place and then we retrieve it from a number of different sources instead of duplicating it everywhere. So you can see here there's any Kafka users, there's this thing called table flow where you can automatically stream it to a data lake. Things like Spark can now read Parquet, read from object storage, and then where there on the right, I'll talk about the plugin concept to change out what you can read from and do search with. So this is an old concept of relational databases where we defined our models, we made our tables, and then as we're thrashing the database, we create materialized views. So we don't start with a perfect solution. We let it evolve, and we let the tools that the database provides optimize it to our use case. And so this is more of I have the software I want to evolve it to fit my business use case. So there are these untapped potential or unused tools that we can then make our current stuff that we're running better. And so I think that, so back up a second here. This is like a logical table on top of the actual table data that's there. And so I think this concept can, if we zoom out to the data architecture level, we have all our data. We don't necessarily want to use it all in the same way. Take that, blur your eyes a little bit, this materialized view concept of I'm going to opt into what data I want to optimize and make it searchable. So let's stop we have to move the whole haystack over to find the needles, whereas now we just go in and with this approach, and it is slower. There is a trade-off here, but you may be stuck with some of your software choices. Adding this functionality to it, I think is a good solution that some of our customers have found. So now let me jump into what is Lucene. Does anybody, by a show of hands, anybody familiar with Lucene? Okay, so this is the workhorse underneath Solr, Elasticsearch, OpenSource, Lucenia. And it is born in 2000. It's written purely in Java, Apache software license. It's funny looking back on doing research for this talk, that 800 gig an hour number was like at one point 400 gigs an hour, and 10-ish years ago, 200 gigs an hour. And so this has been just like a constant evolution, and there's a ton of 24 years of hard work at compressing and efficiently storing data. And the main basic concept is the inverted index. So on the right there, instead of like a relational table where you have your row data, this is what data do I have, and tell me what documents it's in. And so this is the same as an index in the back of a textbook, where I know what I'm looking for. Show me what all pages I can go read on this concept. And so there, just to show you how broad Lucene is that it's been copied into other environments. There's a project called TantaV, which is a Rust implementation of Lucene. And I believe that's what powers the faceting in PG search. So this same concept and approach is being copied across other projects. to bring it to other use cases if it's not a Java use case. So when is Lucene the right tool? When would you use it in addition to the side of, or maybe in replacement of other data stores? And so what it's great at is rank searching on phrases. Your users don't write perfect queries, so being typo tolerant is something that it's very good at. You make multiple indexes. You may find you want to search across both of them, and so multi-index search, sorting, nearest neighbor. So this is, things like vector search. So my colleague gave a talk on some vector search enhancements yesterday. So there's a lot of growth there. Ranking models. So how do you actually analyze and rank and score your results on your queries? And then configurable storage, which is what I'm going to talk about today. So just a quick touch base, row versus columnar. So Postgres, MySQL are row-based formats. Columnar, things like Redshift, Bigtable, they're kind of opposite ends of the use case where, if I have a new row, I just add it to the end. Columnar, I have to, get very clever about shifting other things around. But columnar is if I want to see the sales prices for just this, or if I want to see sales price across 1 million documents, these are all stored in a contiguously on a disk. I just scan there. Whereas a row-based format, I got to go find each row and pluck that one field out. So they're kind of opposite use case. You may have heard like OLTP. So T is transactions. The OLAP A is analytical processing. So these things are complementary to each other, and I'll talk about how Lucene actually does both here. So Lucene has this concept of store fields. So when I ingest a document into Lucene, it doesn't just make the inverted index. It now solves many different use cases. It'll build these on-disk formats, and one of them is called stored fields. So this is basically your row-based access pattern, and this is good for, I want to pull back my original document. I was talking to somebody earlier. If you turn this off, you cut down your storage size, because we don't necessarily need to always keep the old document. If you do want to retrieve the whole document, like some of the search engines do, you pay that disk cost. But if you're really cost conscious, you just index the important parts and it'll tell you what document it's found in. So there is a trade-off there, and hopefully we can help make that clearer to fit within others' budgets. And basically a good way to remember it is it's a good way to get a lot of fields for a few documents. And so this other concept, stored fields, so this is a columnar representation. So if you ingest a document, it then also builds, oops, am I on the wrong? Oh, had an animation there. Okay, so this other format, doc values. So this is a columnar representation of the document where the values are stored contiguously across a bunch of different documents. So now when you go do sorting, faceting, some of these other types of queries, this is leveraged to obtain like a faster retrieval result, and it's the same as a columnar use case where I can scan across all the values for a field. So to the opposite of the stored fields, this is good for grabbing a bunch of values from a bunch of documents for a couple fields. So GeoParquet. So Parquet is a open source file format. I think it's about going on about 10 years now. Started by Twitter and Cloudera. There are a number of different clients, so you can read it from almost every language. It's column oriented, which I think is because things are broken up into groups. So it's not truly columnar across the entire storage format, but it's broken up into sections of row groups, where then internally to each row group, there is a column representation. So this is, and this is good because it's kind of a hybrid of use cases where you can find your rows faster, but you also get some of the benefits of columnar reads and compression. So a neat thing about our big performance improvement in Parquet is you don't have to actually scan the whole file. You jump to the orange section and you read the file metadata. And so this file metadata contains metadata and stats about each row group. So when I go and I'm looking for the needle in my haystack, I go to my row group metadata, and if I'm looking for the number 12, the row group metadata will say, column A only has values at a minimum of 14 to 25. So if my value is not within the metadata, the stats about the row group, I can just skip that. So you can live by and die by how you write these row groups. So if you over optimize for one read use case, there is a penalty to pay where you may have to go scan the other row groups much larger than you originally expected. So there is there's two ways to store data. There's build a dictionary and then plain encoding. So there's a dictionary encoding and a plain encoding, and you can turn this on or off based on your use case. But here, let's say we have FOSS4G NA locations. They're repeated. We can get rid of that by building a dictionary. So instead of storing St. Louis twice, we just put 1-1, and Portland 3 times, we put 3-3. Then there's another process called run length encoding where we're just going to store that value once and then say how many times it repeats. And so you can see the number of characters on the left to represent the cities of FOSS4G NA to what's on the right. Imagine that getting really large. You would have quite a bit of savings on a percentage basis. So GeoParquet is a convention, and what I mean by convention is you name your row and you kind of use it in a certain way. There's not you don't have to. If you do it this way, other formats that don't know about GeoParquet can still use your file. So the customary way is to write a geometry column, and for most of what I've seen, you put a WKB in there. But so there's a bit of there's a trade-off here where I have two boxes on the screen, and left, we'll call it box 1, and on right is box 2. If I want to say, give me all the points that are within the park, and my boxes are too large for this use case, so the park is the middle green section. And this is I'm setting this up as an example that's, for my use case here, but you can't shoot yourself in the foot here where you have a bunch of data that is nowhere close to the park, but you have to scan through it. And since it's WKB and it's stored as a byte array, you don't have column stats on it or the row group metadata stats on it. So you kind of have to load it. Well, a way around this is that you might use it's like the Microsoft Buildings data set that comes out as Parquet. They put a quad key. So you use a quad key, you scan the quad key, and you see, okay, do I have values that are within this quad key? So that's taking advantage of the stats, but that is me writing extra data in a different format to represent my my WKB values. And so I guess I kind of talked about predicate push down here, but this is just the concept of using your ranges and metadata statistics to filter out your data quickly. And you can use dictionary compression. There's several different optimizations you can take to speed up your reads after you write your Parquet file. And also you can just write it in a different way. So if you choose your row groups to be optimized with smaller boxes, then you can run smaller queries more efficiently. So I gotta go fast here. So reindex by query. So back to that materialized view concept of we want to search on our Parquet data, and this is gonna be slower than ingesting our data and searching on it. But this is the point, is that you know that it's a slower use case. You create an index that you point at a Parquet file, you run a query over it, and then you say the results that come back from that, turn that into a search, like a fully indexed search index with all of Lucene's optimization goodness. And I know it's a data set that I want to use, and I'm going to optimize to make it searchable for my application. So there's some documentation on this, and anyone who's asked me about it, we can talk later. You create an engine plugin, and this engine plugin tells is an alternative that when a new index comes in, if it's labeled as a Parquet index, this engine plugin is going to get loaded, and it's going to know that it's looking for a Parquet file on, say, S3 or object storage. And you write an action plugin, and so you're probably maybe familiar with this REST syntax, where here I'm registering a buildings index, and I'm saying use the Parquet codec, and let's use this file on S3 to serve my data. So then the convention that I'm using for this is the row ID, or the nth row in a Parquet file is the doc ID in the search engine. And so this is going to use that stored fields concept where I want to pull back the full document. I'm swapping out, I'm implementing stored fields with just using get this row from Parquet. And so really what this is that Lucene has all these checks around index integrity. And so we have to satisfy that by writing these files out that Lucene is expecting to see there. It doesn't know that we're tricking it into reading a Parquet file. So what we're doing is we're writing where that file is and what the settings are and how you connect to it, and metadata about the file that we got from the Parquet metadata, put it in the file. That way when you go restart your computer, it can reload all those files from disk and make it searchable again. And then I got a minute and a half. So Lucene has this is called a codec. You're probably familiar with like MP3 codecs. This is how the actual data is encoded on disk. So we extend the latest Lucene 99 codec, and we, when it's things that doesn't support, it don't make sense that we want to get from our Parquet file, we then take it and, hijack that call to then be fulfilled by Parquet. And so stored fields, I talked about, that's your row-based format. Something called stored field visitor. We populate that stored field with each column in our Parquet row, and then doc value is the same. We can just scan a bunch of columns. This is awesome. Go through a row group, pull back a whole column chunk, and add it to a doc values request. And then we can query data just like any other index. Again, slower, but if you want to make it faster, you want to opt in to duplicating that data into your search engine, then you can do such. And here we can submit spatial queries around those rows and leverage the WKB and quad key fields that are, in this data set or other Parquet data sets. So I got 1 second left, and that's it. So take questions. I can take.